Welcome to Swansea. Thanks for the introduction there, Chris. My name is Dr. Mark Coleman and I am a materials science lecturer at Swansea University, and I also run the outreach and public engagement events as well as the admissions to the university. So today's session is all about material science and, more importantly, the structure and microstructures of different materials. Now, why do we use that word microstructure? I mean, we can see structures all around us, right? If you look at a tree has a structure. It's got the bark, it's got the sort of the crown and the branches and the leaves of the tree. If you look at a building is a structure, so you can see that. Now, microstructures, there's a little hint in the word there, need microscopes to be able to see the structure down at really sort of small levels of detail. And so what we do as materials engineers and scientists is we explore the link between little changes that we can make to these structures down at quite small levels, and then we can see what happens then to the properties of those materials. So in the chat box now, so first chance to use the chat function, okay, on the webinar today, let's list a few what we think of properties of materials, okay? So I'll start us off, just dump it in the chat. I'm going to say hardness is a property of a material. What are the properties? Oh, Math's got a good one there, ductility. So that's a good one, Math. So what other ones can we... And they don't have to be sort of scientific, you know. Squishy is a property. That's a very technical term there, Emma. That's a nice one. Viscosity is a good one. So really important when you're looking at fluids and glassy materials. Math, that's a good one as well. Malleability, conductivity. Conductivity is a good one. So I'm working on a research project at the moment all to do with electrical conductivity of steel, for example. And you can see how important that is for things like the electrification of transport at the moment. So really good ones on the chat. Yeah, well done. So what we're going to do today is I've got lots of different materials kind of scattered about the office. You might see me disappear off camera and come back and grab some other bits and bobs, okay? So we're going to play a game, right? So I'm going to start off by zooming in quite high magnification on my microscope, and I want you to start to guess in the chat what it is we're looking at. Now, before we do that, I'm going to sort of give you some ideas of things and strategies that you can use to sort of help you guess what the material is. So, first of all, let's talk about materials engineering, okay? It actually encompasses lots of other different types of engineering disciplines and sciences, okay? So, today you're going to have a real broad look at different materials. We're going to have a look at some biological samples. We're going to have a look at some metals and polymers, okay? So it's not just sort of what you might consider as metallurgy, okay, which is historically maybe where material science has come from, but where we've come to now is very, very different. So it covers all of these different topics. So this is what I want you to think about today. So this is what's going to be in your mind, okay? We're going to have a look at the structure of a material and how that's going to affect some different properties. So Pearl and Grace, Matthew, there you had some of these, yeah? Mechanical properties, that includes like hardness and ductility and all those different things, malleability. But we also had a few people there saying electrical conductivity and magnetism, okay? And so it's the bit on the left in green. That's the bit that we're going to look at today. And so you can have like I mentioned here, big components, okay? And you can see the structures for themselves, like a building. But we're going to be down here. We're going to be in this microscopic environment. And like Chris mentioned there as well, in his video at the start, in the intro, before the intro, sometimes you need to go down to the atomic level. So you need to use electrons then in an electron microscope to zoom in even further. So this is where I sit. This is me. I'm happily sitting here in the middle, and I can understand the difference here between these two. So when you look at things under my microscope, have a look at the color of them if they're shiny or dull, and start to think about these three broad categories of materials. Okay, so you've got metals. What do I mean by polymers, by the way? What's another word you can think of instead of using polymers? What can we say as a polymer instead? I mean, there's a picture of something there, for example. Yeah, Lee, we can say plastics. And then ceramics here as well. We haven't got many ceramics today, but we've got a few, and we'll look at some of them as well. Now, there's some other little cool niche groups of materials that we can look at. We can look at composites, and that's a mixture of 2 or more different materials. And then there's some other quite niche ones where we have biomaterials. We'll have a look at some of them today, and some semiconductors. So let's have a look at our very first microstructural image of the day. Can you all see that? What do we think that is? Answers in the chat. It kind of looks like a smiley face. Mrs. James is saying it's a plastic. Yeah, not wrong. Oh, Maria, that is a fantastic guess straight away. Let me zoom out a little bit. Kind of looks like a little crab. It's actually branded on there. Oh, and here we go. It is part of a microchip. Okay, and we actually use microscopes like this in the department, and people use these in industry to look at these little microchips. And what they do is they sort of move the circuit board around, and you can zoom in on some of these little solder joints, make sure there's a good connection there. And then so you can automate this as well, and so you have some of these on production lines. So good guess there, Maria. Does the X-ray... Do you use X-ray? Yes, Matthew, we do use X-ray machines as well in our department. And so what you can do with something like this is pop. It's a USB stick, by the way. It's a USB stick cut in half. You can put that in an X-ray CT machine. Something like this is really cool, actually, because you've got lots of different materials on here. So you've got the metals as part of the solder. On the left here, you've got the plastic casing. You've got a composite board making up the circuit board itself. And then you've got the paint pigments then making up all the markings. So in an X-ray CT machine, Matthew, this is really, really nice because you've got different densities of materials, and it shows really, really cool 3D tomographic structure. Good question there. Okay, so we're going to stick with sort of electronic devices, and most of you, I think, are probably watching me through an electronic device. And so let's pop the next structure under the microscope. I'm going to defocus it deliberately, and then I'm going to try and get this into focus while you're watching me live. Oh, no pressure. So, what you're actually seeing now when you're watching me, if it's on the webcast or on YouTube, is this is what I'm made of. Yeah? I'm made of thousands or even millions of pixels. And those are pixels right there. So can you see, hopefully you can see on the screen, there are 3 major colours. The 3 sort of primary colours here, the RGB colours, yeah? The red, the green and the blue. So Matthew, if I was to zoom out now on this region or defocus it slightly, what colour do you think this would look like? So we've got quite a lot of red still in these pixels. We've got quite a lot of green still in these pixels. And we've got still quite a lot of blue. Ah, so Mrs. James is on point here. Yeah, it's actually white, Lee. Correct. So if I defocus it and zoom out slightly, it actually looks white. And that's because white light is made up of all the colours of the rainbow. So if you go into your science classes in school and you put a little prism on your on a light source, and you'll see there's sort of rainbow scattering of all the light. Yeah, and it's because you can see there that was the white region of the Discover Materials Instagram page. So if we looked at, say, like a nice orange or red region, here we go. So there's the Discover Materials little T section. If I was to zoom in on that, what pixels do you think we'd see? Do you think we'd still see the blue ones and the green ones? Well, predominantly they're still there. The pixels are still there. It's just the blue and the green are sort of switched off. And as I focus in and very slowly, you can see on the left there is actually a little bit of two colours. It's predominantly red with a little bit of green, but it's the absence of blue. Okay? And so what we do, Matthew, is we change the mix of the three colours, but we also change their intensity as well. So you have some polarization going on here, where you can actually turn on or turn off the little pixel and allow some of that colour to come through or not. And you can play around then with the different colours that you get if you zoom out. Now, if you've got a really nice telly at home, you've got something that's a 4K TV like this one I've got behind me here, all that means is you've just got more pixels that make up the same square area of image. Okay? All right. Oh, this is good. Now, yeah, good question in the chat. So yeah, so in sunglasses, there is some polarization going on, right, to allow not all of the sort of wavelengths to get through and hit your eye. So yeah, great question. Okay, moving on. So those were kind of digital devices. We had, you know, the USB stick right at the start. We had my mobile phone screen. Let's go completely the opposite direction. Let's look at biological materials. And we do this in material science, by the way. So we look at samples that Mother Nature has made. And as engineers, we look at them and think, well, is there something that we can learn from all those years of development and evolution? Is there something we can borrow and apply to some engineering problem? So I'm going to zoom in on this one, and I want you to try and tell me now what this is, right? So let me get this in focus first. We need a little bit more light. Here we go. Eleanor, the Q&A button or the chat should be in one of the toolbars, either at the top or the bottom of your screen, depending on how you've got your screen set up. Oh, so Mrs. James is saying this is a fish. What do we think, everybody, in the chat? Yes or no? Oh, a leaf. Maria's saying a feather. So it's definitely got a structure, right? There's a definite pattern here. You can see you've got something quite thick, then something thinner, and then something thinner still. So let's zoom out slightly. Mr. Hill says a feather. Oh, yes, it is correct. This is a feather that I found at Swansea Beach. This is from a seagull. Okay, I didn't actually take it from the seagull itself. He wasn't a very unhappy seagull. I found it on the floor. And so you can actually see here now that it's got a very strong structure. You've got a quite rigid central shaft. You get these structures then coming off that. And again, then you get another structures coming off that. So quite lightweight, and it has the ability to stay stiff, but some flex in the material as well. Okay, so moving on to the next one. Let's have a look. Everybody likes these ones, okay? This isn't something that we normally look at in material science, but as I mentioned before, what we can do is look at some of these structures and borrow the ideas and apply them to engineering problems. So let's have a look at the next one. There we go. So this is a little centipede that we found just outside the department. And so the cool thing about these types of these insects is that they wear their skeleton on the outside. That means that they can be really, really strong and difficult to sort of hunt. But it means that insects can't really grow very big because it's quite energy intensive to have your skeleton on the outside. And so what types of materials do we use that have skeletons on the outside? I mean, if you think about this, let's have a look at this bug. You can see it's curled up. But look, it's got this lovely structure. This sort of armor plating on the outside. But can you see that the armor plating itself has got a substructure? And so you can see how this insect has grown and the direction at which that armor plating has grown. And so let's have a look at another bug. Let's go over to the next one. Most of you should be able to get this. Most of you should be able to get that. Anybody want to guess what type of... It's a bug, by the way. Anybody want to guess what type of bug that is? Oh, Emma got there straight away. Correct, Powell. It is a ladybird. Okay. And again, ladybirds have these lovely structures where you've got two sort of armor plates either side, and it hides the wings. I think you can actually see maybe one of the wings is poking out the back. Yeah, there you go. Actually, two of the wings are poking out the back. And the nice thing about ladybirds is they have this thing called a compound eye. And that's made up of lots of little eye sensors. Oh, I think I've got silver paint on it by mistake, but it can be really, really cool to look at. Right, let's do a couple more. Right then, what about these? These are very, very small, by the way. Let me get the correct magnification on here. So I'm at 1 times max. So let's put the correct scale bar on. So that scale bar there now is live at the bottom. So that gives you an idea, Mrs. James, of the size at which these things are. Okay. Oh, so Alice is saying, are these fungus? Are they mushrooms? Yeah, okay, let's zoom in then. Let's have a little look. Let's zoom in. So let's choose the bigger of them here. Let's zoom in on this one. So let's see. Lee might be onto a good one. Lee is saying they actually look like shells. Yeah, they are. They're little shells. They're little animals found in the sand and the seawater at Swansea University. And so what we can do as engineers is we can use some of these structures. Let's see if we can go on to... This might be a little more familiar to you. Here we go. Let's change the light in a little bit. There you go. Yeah, so they're little crustaceans, okay? They're little shells. Let me get the right. I'm on 3 times mag, so let's change the scale bar there. So look at the size of that. It's less than 1 millimeter big. And you find these sort of all floating around in the seawater, in sand. And what we can do as engineers is these little structures here. There used to be a bug living inside here, by the way, yeah? But these structures have grown to be able to sort of filter water and seawater inside and out and filter them so the little crustaceans can put their feathery tendrils out, grab some of the plankton and have some breakfast. And so what we can do is we can use the shape of these shells because they're really efficient, and we can model then how water flows through the shells. So if you want, for example, then to make an underwater turbine to make some clean sort of marine energy, starting with a design like this would be really, really useful. Okay, lastly, I wonder if you'll get this one. This is quite a tricky one, okay? This is quite a tricky one. Let me change the light in a second. Give you a chance here. I don't want to zoom out too much. Oh, there we go. Oh, there's a detailed question in the chat there, Math. I'll answer that while people are having to think about this one. Do you think Apple or other companies can design phone cases for their mobile phones? Yeah, so a lot of companies now are developing phone cases that are more shock resistant. So if you accidentally drop your phone, for example, you're not going to smash your screen. So a polymer, for example, is a really good material for that because it's quite cheap. You can form it into lots of shapes for your mobile phone casings. But it's also quite ductile. So when it has some impact damage, it can disperse that energy and not damage the internal components of your screen. Now then, your second part of the question there is really good. How environmentally friendly are some of these products? Well, in terms of using metal products for different things, metals can primarily be recycled quite easily, especially for things like copper, which are normally quite pure, and steel. But polymers, not so much. They don't really degrade that well. There are new areas now of polymer research that are designing polymers that can actually break down. All right, so Mrs. James, so this was the last guess. A glass beaker. Yeah. Mr. Hill is asking, is this a nail? A glass or a bug wing? Yeah, so it's quite tricky, isn't it? There's a quite varied couple of guesses there. So let me zoom out a little bit. Can you see that there's a structure to this material, all right? It's got like, it kind of looks like the feather. It's got different layers. And in between those layers, it's got, again, these little sort of strands coming out. Zoom out again. What about now? Do you want to have a second guess? Yeah, Matt. So a lot of companies now are working on biodegradable polymers. And so I know somebody here, for example, is working on a plant pot. So essentially what you do, if you have a Christmas tree for Christmas and you have essentially a plastic plant pot, if you then plant that plastic plant pot into the ground, the plant pot itself will degrade and actually release some nutrients then to feed the tree. How cool is that? Okay, I'll zoom out a little bit more, put you out of your misery. This is quite a tricky one. This is actually part of a cuttlefish. So a cuttlefish, you see some of these sort of white bony residues washed up on the beach, and if you've got parrots or birds, you can actually give these to them and they use these to sort of sharpen their beaks. So the shell itself of the cuttlefish is this bit here on the top. It's this little bit there. And then this cuttlefish has this layered structure. So Matt, when we were talking about packaging materials or withstanding impact damage, you can have a look at something like this type of material, because when a cuttlefish has some impact to it, it actually fails one layer at a time. And so it's developed this system to protect its vital internal organs. And so it sacrifices one layer at a time, like a block of flats. Like one layer will collapse first, but the other layers will be fine. And so it does it in turn. It does it sequentially. And so we can learn from that to develop cool materials. Yeah, it's like a buffer. And so it'll take time for that damage to kind of go between each layer. Okay, what should we look at next? We'll stay with biological materials for now, because they look really nice under the microscopes. And we'll stay with something from the beach. And so I'm going to zoom in here, see if I can get the nice, there's a really nice section on here. Now there's a bit of everything on here, okay? But I want to focus in on just one part. Anybody want to guess what that might be? I'll give you a clue, it's from the beach. There's a bit of a theme going on here. Zoom out a little bit. You can see little grains of sand. Oh, yes. Yes, Lee. Mrs. James has got it. These are barnacles. These are little tiny barnacles. Let me just adjust the scale to get the manual scale. There you go. So it's about 1 millimeter wide. These are little barnacles. And actually, I've done a research project on the structure of barnacles. They're really cool. Can you see it's made up of different plates? Let's zoom back in. The actual barnacles themselves open and close. So there would have been a little barnacle creature living in there, and it would send little tendrils out again to feed on the plankton. But can you see it's made up of different plates of material? Little plates of calcite, and these plates, when they join together, they have a very, very interesting mechanism that allows them to sort of open and close. Like if you've ever gone to pop a barnacle or a limpet off of a stone, it kind of hunkers down. yeah, it kind of pulls its shell in and it kind of says, I don't want to leave, I'm happy here. And you have to really get something to sort of pop it off the shell, pop it off the rock. And that's because the shell structure can actually move slightly. And that's really interesting in where you want some mobility in some instance, but then you want to be locked into a rigid position in other examples. And so for things like prosthetics, that's really, really interesting, because if you're walking, for example, you want your knee joint to be really sort of mobile and you can sort of walk along using your prosthetic. But then if you're standing for a prolonged period of time, maybe you want to have your sort of leg locked in position so you can put more weight on it more steadily. And so there's some research going into that biomedical side of that. And again, using sort of Mother Nature already as examples. Okay, I'm going to put a few more under the microscope and then we'll move to some metallic materials. So, it's winter season, so I want to show you, I'm going to change my microscope now. So instead of having light shining down on all our samples like what we've just been doing, I'm going to have the light shining up. And so this material is thin enough to allow the light to actually pass through. So just allow me to change this slightly. You've still got to guess what it is though. Some of you might get it first time. Think about the colour, think about the structure. Is it a polymer? Is it a composite? Is it a metal? Here we go. What do we think that is? So that the light is actually passing up through the material. So Matthew, you wouldn't use the actual barnacle or the calcite itself to replace titanium joints, because calcite would end up being actually dissolved inside the human body. So you would have to use something that would resist being attacked by the immune system in the human body. Oh, Grace has got it. So Grace was there. Someone's saying honeycomb structure, resin or skin. Yeah, it does. It looks kind of alive. Okay, so if we zoom out now, it looks pretty dry, right? Pretty furry. This is actually a skin. This is actually a leaf picked up on my way, literally from the floor, walking into work this morning. It's very thin. You can see the light is passing through it in some instances. That's because all of the pigmentation, all of the energy, all of the goodness has been sucked out of the leaf. So there's the kind of brown, curled up, dried up leaf. Let's put a green one. Let's put a one that I actually took off. Look at how lovely that colour looks instead. So this has still got pigmentation in it. It's still got the network of veins taking nutrients to and from the leaf. Very, very different. Now we see some of these structures in nature, where we've got, somebody said a honeycomb structure just now in the chat. Really, really interesting structure. We see some of these types of structures in metallic materials as well. So keep this picture in mind here. This is the leaf, and these leaf sort of veins have this structure to them, right, where they have this network, right? So if you were a sort of nice bit of sugar, you've been made in the leaf, or some energy, you can travel up and down these veins. You can go off on these junctions. Can you see these junctions mostly have 3 roads joining them? They're called triple junctions. You can see there's one there, look, there's another one there, and mostly you get this in nature. Okay, this very, very energy efficient to have structures this way. Well, we see these in metals as well. Before we do that, let's have a look at another form of triple junctions. So here I've got a petri dish, and all that's in this petri dish, it's not very technical, are soap bubbles. So I've lost my little soap bubble squeezy thing. There it is. I'm going to make some more soap bubbles live during the stream. And when soap bubbles join together, they form these triple junctions too. Can you see that? Now the cool thing about the soap bubbles, can you see those little bubbles traveling along the interface? Can you see those bubbles on the top there traveling along the interface? You get this in metallic materials. You get this type of structure. And I'll show you an example of that in a second. Can you see those little bubbles? How they're sort of wanting to travel up and down these interfaces. And again, when these bubbles join together, they do so using triple junctions like this. And this is very, very energy efficient. Now, if all of my bubbles were the same size, I would make a honeycomb structure. And the bubbles would have 6 sides. But you can see this bubble, for example, has got 5 sides. And some of them will have 4. And like if I see if I can find one that's got 4. Oh, there's one. It's kind of like a square one, but it's got some curvature. It's still got a little bit of curvature to the interface. So, hang on, Mark. You're telling me that metals have this bubble-like structure? Well, they do. Oh, Matthew's saying, I presume a triple junction is similar to those seen in graphene. So graphene is a slightly different material. Graphene is made up of something like this. So this structure here, you would have carbon atoms all joined together in this triple junction, like you said there, Math, on one plane. But with graphene, what we do is we essentially take this top layer and we peel it off to leave ever thinner layers until eventually you're down to only a few atomic layers thick. But essentially you're right, in this plane here you get these hexagons, and so in graphene you get these carbon bonds, and each triple junction's 120 degrees in angle. Okay, cool. Right, moving on. I was going to show you how these look like in metals. But before we do, we've got to understand what metals are made of. And so to do that, I'm going to ask you to identify another material. Now this is something you should all be familiar with. You might guess it straight away. It looks very festive and wintry. So Eleanor's saying salt, Mrs. James is saying salt. You're very close. I've got one of each. Mrs. James is saying ice. Ah, she's got it finally. So this is sugar. Do you want to see salt? It's very similar. Okay. Salt crystals. They're a bit finer. This is literally table salt. So, the cool thing about salt and sugar is they're made up of crystals. Okay? And what you see in when you look at grains of salt or grains of sugar are individual crystals of material. Now, crystals mean that it's gone from a liquid and then solidified into a solid, but the atoms in that solid have some structure to them. They have some pattern to the atomic arrangement that means they form a crystal. Okay? And so, that's what we're looking at here for the salt and sugar crystals. Now, metals do the same. Metals actually start off as being liquid, and then when you solidify a metal, it forms crystals of solid material. So here we go. Can you see that on the webcam? Let me stop sharing my microscope. Here's my webcam. This is a thin sheet of steel that's been galvanized. And you can see these on the sides of motorways, on lampposts, or if you've got like an old galvanized dustbin, you can see this crystal structure of grains. Now what that means, in each of these grey regions, a crystal has grown. And so in one of these grey regions, the atomic structure is lined up like this. And one of the other grains, the atomic structure might be lined up like that. And that means that it catches the light differently depending on how the lattice is arranged. And that gives us this lovely sort of grayscale contrast that we can see. Now, this is like an extreme example, but most metals, if you polish them up so they have like a mirror-like finish, you can see the microstructure of these grains. And so I've got a few examples here. This is a piece of steel bar, and it's been polished to look like a mirror-like finish. And so let's pop this under here and let's see what this looks like. So what we do with these types of materials is we mount them in this black stuff that I've got here. We polish the sample so that it has this mirror-like finish, and then we burn it on purpose. We etch the sample. And what etching does then is it reveals that atomic layer at the start so that the sample can catch light differently. So now next time you look at a metal, don't want you to think of the metal as being one giant just block of copper or aluminium or iron, but little crystals all joined up. And where those crystals meet, you have a boundary, a crystal boundary, or a boundary between those two grains. And that's what my area of research is in. It's in these cool areas where crystals join together, because when you look back at the salt that we were just looking at, sorry, not the salt, the bubbles that we were just looking at, you can get things traveling along these grain boundaries. You can get corrosion happening on these grain boundaries. So can you see there's like a little, this is iron, by the way. Can you see it starting to corrode? Can you see all these browny golden flecks? That's actually corrosion product. That's iron oxide now developing on the surface of the material. Gloria, yeah, the session's being recorded. I think Chris is, like he said earlier, he's going to break up today's session into snippets, and he's going to post them on the Discover Materials webpage or the YouTube website, for the YouTube account for us, okay? Okay, I'm running out of time, so I want to sort of talk a couple more samples here. So those were crystalline metallic samples, and you can also have other crystalline type materials. So I stole this from my son's bedroom the other day. He likes like rock collections. So these are those kind of rocks you can get in little chemistry sets, these little rock collections like an opal or something like that. So if I pop this on here, it's actually quite a transparent material, even though it's a solid and even though it's crystallized. And then some of the detail that you can see, the color comes from, on the pigmentation, comes from the impurities in the crystal. So you can see all these little bits trapped in here. It's actually a little bit of stone trapped in there. And we can do something similar with glass. Now, technically, glass isn't really a solid. Okay, it's a glass. You could call it a supercooled liquid, perhaps. It hasn't actually crystallized. But you can, again, add pigmentation to glass to color it. You can layer it with different materials. Or you can turn it into a composite by adding a polymer layer and have a glass windscreen, which is really, really super strong and tough. So I'm conscious I'm running out of time. I'm going to show you a few more materials. I want you to guess this last few. So these are more everyday materials that you might find around the house. Okay, so let me zoom out. I'm going to stop share a second because I want this to be a good guess. Okay. Now think about all the things we've looked at today. We've looked at polymers, composites, metals. We've even looked at some fluids with the bubbles. So I've got a bit of a tricky one here now. See if you can guess what this might be. Ready, steady, go. Quite colourful, right? Really nice and pink. Any guesses? Oh, soap is a good one. Washing up liquid. Mrs. Harriet Jones is saying it is a polymer. Matthew's saying detergent. A Haribo. Oh, that's a good guess. Not quite. Let me zoom out a little bit. Oh, Mrs. James is getting there. Mrs. James is on fire this morning. Keep on zooming out. Here we go. It is actually a sponge. It's little bubbles. So what we do with a sponge is we make a polymer and then we blow bubbles through it and then we let it cool, and so you get this spongy layer. The good thing about this though, Mrs. James is taking credit for all the class answers, is she? Okay. So the good thing about this is that these bubbles don't actually join up. So let's zoom back in. So this is kind of the opposite of the bubbles. So where we had the bubbles, we had a bubble of soap. Here we've basically just got the network that's left over. So what we can see here is just the polymer network left over. And the nice thing about this now is if you fill that with water, it will hold all of the water and soap. And then when you go to squeeze it, all that soapy water will come out. And so you can use that then to sort of wipe the dishes. Okay, so let's have a look at a few more everyday household materials. Okay, so you did really well on that one. I thought you weren't going to get that one. Okay, last couple. We're running out of time. Oh, I just realised some people might have seen a sneak peek of that on the... Let me switch to the share screen then before. Zoom back in. It's quite a tricky one, this one. I wonder if you'll get it. Turn that off. Let me zoom in. Okay, can you see? Guess what that is? What type of material do you think that is, first of all? Plastic? Metal? Do you think that's a ceramic? Oh my God, Russell! You must have seen it on the webcam. You must have seen it on the webcam, you guys. Someone's saying a spoon. So it's definitely got bristles. There's some white bits and bobs kind of dotted around. Oh, there's some sharp eye students, is there? Mr. Hill. Okay, it is a toothbrush. You can see there's bits of hair in there. And like bits of undried toothpaste. Okay. There we go. So there's my toothbrush. It's not too bad, okay? But what we do is some of these materials now, so you can make strands of plastic like this, and you can set it in a stronger material, and you can make different composites, for example. Okay. I think we're running out of time. I had loads more to show you, but I'm gonna stop it there. And just summarize what we've been up to. So we've used a microscope today, and if you've got one in your school, sometimes you might use a microscope for like biology class, and so you might be used to having things like this, you know, in a slide like that. That's fine. These are normally used then in transmission. Okay, put other things under the microscope. Put your finger under there. Okay, do you want to see my my skin before we go? Like, just stick your clothes under there. All sorts. Have a look at the structure. How clean are my hands? Look at all the little bits of hair on my finger. Can you see? Because I've got a jumper on. Can you see the structure of my hand? Can you see all the little pigments in my skin? It's really cool then. You can actually see sometimes if I'm warm, my skin will start to sweat. Put other things under the microscope because it's really interesting to look at the structure, and then as a materials engineer, you start to understand then how the structure can affect all those different properties that we were talking about at the start of the session. Okay, I think I'll end my section there and I'll invite Chris back in. I'm happy to stay on for any other questions. I think there's a Q&A session as well later on in the day, so I'll be part of that. If you've got any questions or you think of stuff between now and then, ask them during that and I'll do my best to answer them for you.